Howdy! This is your friendly neighborhood physics teacher here, and we're here to learn about torque. Now, what torque is the turning effect of the force. Turning effect of a force. Now, that could be any force. It could be any force we've learned about. It could be force of gravity. It could be force applied. It could be force of friction. It could be any type of force, anytime. We've talked about it, force of spring, force of tension, any type of force. It's just a force. It's the force that causes an object to rotate or turn. It's the force that causes an object to rotate or turn. Now, of course, the two things that affect it, one of it is the amount of force. The more force, the more torque. And the distance from the pivot point. Now you're asking yourself, what is a pivot point? A pivot point is where the object rotates. Where the object rotates. We have a wrench here, and it'd be right here would be the pivot point. Because if you actually grab a hold of that wrench and start rotating it, start moving it, that would be where it starts to rotate. That would be where it, that's the pivot, where it starts to pivot, where it starts to turn. The next example we have is a door. Now first, we need to figure out where the pivot point is. Where is the pivot point? Hopefully you said right here, where the door hinges are. So this is the pivot point. Now remember, I told you there's two things that affect torque. One is the amount of force. The other is the distance from the pivot point. Now let's say both of these forces are the same. We have a twin on one side and a twin on the other. So twin 1 is trying to push the door. And he's on the outside, he's on the inside of the house trying to get out. And twin 2 is trying to be silly, be funny, and trying to keep twin 1 inside the house. Which way would the door rotate according to twin 1? So if he's pushing in this direction, that just means the door is going to rotate that way. And if we're looking at twin 2, he's pushing this way. So the door would end up turning that way. So we kind of have a clockwise and counterclockwise method going on here. So think about if this wasn't just a normal door, it was one of those really cool spinny little doors you have in some of those fancy hotels and restaurants. And think about which one would be clockwise and which one would be counterclockwise. Hope you said one would be clockwise, because if you look at it, it's going the way the clock would go. And this would be counterclockwise or anti-clockwise. It's another way you can say it. So this would be anti-clock or counter-clockwise. And this one would be clockwise. For ones that need to kind of visualize what a clock, remember you have a clock, just 12, 3, 6, 9. And when you have your hands go, when your hands rotate this direction. So that's why it's considered clockwise. And then, of course, the opposite would be anti-clockwise or counterclockwise. Bless me. So knowing where the pivot point and knowing which way the force is trying to turn the object are two very important things. So I know how to say that's, which one's the pivot point, and I would know how to know if it's going counterclockwise or clockwise. So torque is a turning effect of the force. Makes the force turn. Just a couple of things. It depends on the size of the force. So the bigger the force, of course, the easier it'll be turned, but also depends on where the force is being exerted, where the force is. So according where the force is. Now, where do you think would be the easiest place to open said door? So the arrow started over here, and it slides all the way down there. Where would it be the easiest to open said door? Hopefully you're thinking about a doorknob. The doorknob of the doors are over here for a reason. Because that's it, you can use less force to open the door. So we already talked about the bigger the force, the bigger the torque, and also the bigger the distance, the bigger the torque. So we both have direct relationships going on. We have direct relationships going on there. So knowing that, which position requires less force to turn the crowbar? So we have one grabbing it way down there. We have one grabbing it at the end of the handle. Where would it be smart to grab the crowbar? Oops. Hopefully you said the blue one. Again, it's the furthest away. Now, we got to think about it. Where is our pivot point in this case? Where is our pivot point? Hopefully you said your pivot point is right here, kind of where the crook of the crowbar is. So that would be our pivot point. And so the further away you are from the pivot point, the higher your torque is. So, and also that means that you can use less force. So that's why you have really, you have those handles on crowbars, handles on wrenches that are really, really long, so you can get further and further away from what you're trying to rotate, what you're trying to spin, and you can use less force. So the turning effect of a force is, there's your equation. This little funky looking T here is called tau. It's a Greek letter. And your equation is just force times distance. And F is, of course, the amount of force, which is what unit? Newtons. And then you have the distance. So D is the distance from the force to the pivot point. From the force to the pivot point. And that is measured in meters. So what do you think? Oh, it popped up. There you go. So the unit for torque is just newtons meters. So you just plug the two together. It's just newtons meters. Very simple. So if you know what force is in newtons, distance is in meters, that is newtons meters. This little thing right here. Oops, I need the highlighter, not the pen. This little thing right here helps if I actually, get the right color. What's going on here? There we go. This little thing right here, except it's wanting to be black. I will block it out. I want highlighter. And then I went, there we go. Geez Louise. That little thing right there is telling you that the force and the distance are perpendicular. The force and the distance are perpendicular. That's what it's telling you. So the force and the distance are perpendicular. It makes a 90-degree angle. If it doesn't make a 90-degree angle, you just have to add one slightly little thing. So it shows force times distance, and then it's sine theta. So if your force isn't at a 90-degree angle to the object you're pushing, so again, if we go back to the door that we were pushing, so, or even here, so this right here makes a 90-degree angle. So we would just have to use force times distance in that case. If we had any type of tilt, we would have to use sine of our angle. And we only use sine. We never use cosine for torque. We only use sine. Again, equilibrium. The world wants to be balanced. It really does. The world wants to go into equilibrium. The world wants to go into balance, but it tries to go into chaos. So something is in equilibrium or balanced if the net force is 0. We've talked about that. Net force has to be 0. So the force that's making the object go equals the force that's trying to slow it down. And also, the net torque is 0. So torque can just be replaced by the word force, because torque is just a rotating force. That's all it is. Torque is a rotating force. And so the torque, like on kid 1, would have to be the same as kid 2 if they were balanced. Another way of saying it is the torque that's going clockwise has to equal the torque that's going anti-clockwise. So let's think about how let's look at this little picture. First, let's label the pivot point. Where is the pivot point? Hopefully you said right there. So that would be our pivot point. Now, what force is causing child 2 to go down? Force of gravity. Remember, I said any force can be a force. So force of gravity is causing him to go down. And the same thing is you have force of gravity going against child 1 as well. Now, both of them are perpendicular to the force, so we don't have to worry about sine or cosine or anything. Let's think about how it's rotating. So again, if this whole entire seesaw could sit there and spin, which way is child 2 rotating? Anti-clockwise. Very good. And then let's look at child 1. If this little seesaw could spin, which direction is she going? Very good. Hopefully you said clockwise. So child 2 would be torque of anti-clockwise. Child 1 is clockwise. So knowing pivot point and knowing if it's going anti-clockwise or clockwise is extremely important. That's why I'm harping on that. So we've already talked about that. So child 1 would be going clockwise. Child 2 would be going anti-clockwise. And those have to be balanced for it to be equal. So again, if you take your pencil and you sit there, okay, so he's going down. If I turn that into a circle, which way is that going? Same thing with the guy. We can do the same thing with the guy. Where's my pen? And the gravity's making him go down. So he's going clockwise. So you need the force, you need the distance from the pivot point, you need the force, and you need the distance from the pivot point. You need those for your problem. So you need to know where your pivot point is, you need to know how far that object is from the pivot point, and you need which direction the force would cause the object to rotate. Again, if it's equal, it's balanced. And you just use your equation. So I know y'all like steps. So here are some steps. So first you need to identify where the pivot point is. How far are your objects from that pivot point? You need to identify all the forces acting on the object, all the forces that are acting in the system. And then work out if it's clockwise or anti-clockwise, which way it's going. And then you just use your equation. So let's do a practice problem. So Hannah is 50 kilograms and the plank is 6 meters. Leo is 1 meter from the end. What is the force of Leo? So let's do a practice problem. So let's do a practice problem. So you know me, when in doubt, draw it out. So we have a seesaw. We have a little girl over here. And we have big scary lion over here. The givens it gave us, it said that the mass of the little girl, which I do not remember the little girl's name right now. Let's go back. What was the little girl's name? Hannah. So the mass of Hannah is 50 kilograms. And the mass of Leo was... Nope, we don't know the mass of Leo. But we know the plank is 6 meters, and we know Leo is 1 meter from the plank. So we don't know the mass of Leo. We know the whole entire plank. We know that the whole entire plank is 6 meters. But we just need the distance from the pivot point. So first, where is the pivot point? So here's our pivot point. So what would be the distance between Hannah and the pivot point? Hopefully you can see that the pivot point's in the middle. So her distance, the distance of Hannah, would just be 3 meters. And they've already told us in the problem that the distance from is 1 meter. The distance of Leo is 1 meter. Now we need to decide if it's spinning clockwise or counterclockwise. So Hannah, it's the force of gravity that's causing her to go down. So which way would she spin? If we take our pin, we go down and think about how, if this is our pivot point, just turn it into a door, how it would cause the object to rotate. So it would cause the object to rotate kind of like that. So that would be a anti-clockwise matter. If you look at Leo, his is his force of gravity, but he's going on this side of the pivot point. So his would be a clockwise matter. So our equation that we would end up using is our force, let's even break it down even further than that. Torque, we'll say clockwise, equals torque of anti-clockwise. So the force, gravitational force of Hannah times the distance of Hannah equals the gravitational force of Leo times the distance of Leo. Now, what is so we have that, but we don't know what our gravitational force. We have mass, though. And then what do we always have? We have the acceleration due to gravity, 9.8 meters per second squared. So we can find our force of gravity of Hannah. Our mass was 50 times 9.8. And you get your handy dandy calculator, and you do 50 times 9.8, and you get 490. Whew. And we don't know the mass of Leo, so we can't find the force of gravity of Leo. That's what we're looking for. At this point in time, we can just plug in. We have the force of gravity of Hannah. We have the distance of Hannah, which is 3 meters. We don't know the force of gravity of Leo. That's what we're trying to find. And we know the distance of Leo. And now we just plug in. Or not plug in, we just solve. We've already plugged in. So we get 1470 equals our force of gravity of Leo times 1. And if you divide both sides to get force of gravity by itself, hopefully you can see that 1 just kind of disappears, and you just get 1470 newtons. So that is a very heavy lion. But that is our problem.